My name is Sarah Gomez and I'm a mechanical engineering senior, and I currently lead the SDSU mechatronics team as president.
My name is Daniel Campas. I am a fourth year undergraduate at San Diego State University, and I am the mechanical lead of mechatronics.
My name is Christian Gould. I'm an applied math major and computer science major at SDSU. I'm the current software team lead of the SDSU mechatronics team.
I'm Alexa, and I'm a software project manager at SDSU Mechatronics.
My name is Tristan Richmond. I'm electrical co-lead for SDSU Mechatronics. I'm also a fourth-year student who's studying computer engineering.
My name is Pierce, and I'm a senior electrical engineering student. I am one of the two electrical co-leads on the team, and my role is to lead the design of our full system electronics, as well as teach new members basic electronic skills.
This year's competition vehicle consists of an aluminum enclosure that is built from individual aluminum plates that are welded and anodized together. The design includes removable input and output panels that can be attached to the sides or the bottom of the enclosure. These panels contain all the cable pass-throughs from the inside of the vehicle to the outside for the applicable systems. The reason for having these panels is to prevent machining the hole directly whenever there are design changes either to the electronics or to the mechanical systems of the vehicle. Whenever such a change happens, we can machine a new panel and replace it with a previous one and prevent any irreversible changes to the vehicle. There is an external frame attached to the sides and to the bottom of the enclosure. This frame allows us to mount payloads and sensors anywhere we want in the vehicle and allows us to change their position later if we need it. Similarly, the inside of the vehicle also has an internal frame for electronics that allows us to either add, remove, or change the locations of the current components without having to drill new holes into the enclosure itself. Our vision system in the past consisted of a camera that faced permanently forward and a camera that faced permanently downward. This year, we have chosen to use a tilting camera system instead of a camera dome, as well as an additional camera that always faces downward. The reason for making this change is to increase our field of vision and prevent any blind spots in case we're tracking an obstacle and suddenly lose sight of it. Our water protection systems have been pretty efficient in the past. However, this year we have chosen to add further protection to the electrical components from the inside of the vehicle as well as to the outside. One example of this is a DVL cap that we have placed on top of our Doppler velocity log. This DVL cap includes two radial seals using O-rings that can impede water that's already inside of the enclosure from damaging this expensive component. Another new feature of this vehicle is a custom-made pneumatics manifold. In the past, off-the-shelf manifolds have forced pneumatic tubing to travel along the inside of the vehicle, creating potential hazards whenever one of the pneumatic tubes failed and water could leak back into the system. This custom-made manifold allows all pneumatic tubing to travel along the outside of the vehicle, effectively eliminating this hazard for the team.
Going into the 2020 RoboSub season, we had to think about what we were going to do for our next electrical system. This was mainly because we were forced into redesigning it since in 2019 our sub went under a catastrophic flooding that caused all the boards to be unsalvageable and beyond repair, including our most valuable sensors. Some of the sensors we were unable to replace, so this forced us to consider cheaper alternatives, which ultimately left us with the decision of making a system that was minimalistic, not over-engineered, and could be easily replaceable and mostly just bought off the shelf. This would be reliable and a good stepping stone for developing an electrical system that would be replicated ideally among multiple subs. By doing this, software would have multiple submarines to test on, which is optimal for progression and testing out code. Now, with the system specifically, the boards that we found that we could just buy off the shelves more related around power. We had DC-DC buck conversions, we had ESCs for each of the motors, and we have a motor controller himself. But the ones we had to design ourselves, those were more fit to specific sensors to fit our needs. This would include using an AHARS board to talk with the AHARS and transmit its data over USB, since that was the common serial interface for all of the boards. Out of all the boards we designed, we tried to keep one thing consistent, which was simplicity and making it usable on our Arduino Nano. We found Arduino Nanos are really cheap and very comfortable for new members to develop on and code on, since a lot of people are familiar with the Arduino function library. and it is also taught in our university. With each of the boards being an Arduino, talking over USB, we also liked the idea that we could use I2C since this was on each of the Arduino boards, so that way we could chain it into a backup protocol for data transfer. When designing a board, we had a new system of development. We used interval stages to progress how we developed the board to ensure minimal debug time and save as much money as possible. Now, when we designed a board, it went through a new system of development. We used interval stages to pinpoint where a board was in its development cycle. We'd start off by drawing the schematic on whiteboard, looking at the theoretical electrical necessities for the board to function. Then we'd transport those whiteboard designs into Altium or Circuit Maker to have a paper version, which would then make a PCB, which could be sent out later. Before we'd send it out, we would test it and debug it on a breadboard. We'd buy the components, see what works and what doesn't, and get comfortable with the design before moving on the next stage, which was using it on a proto board. When it was on a proto board, we would solder the components, test fit it, see how things work in close regions to each other. Then we would outsource our PCB to be made and milled, and then come back to our location where we populate it ourselves and give it one last test fit and debug to make sure it's fully functional and ready to be put into the submarine.
So we designed the software system to be hands-off. The idea was that each component be touched as little as possible. To accomplish this task, we decided to treat the sub as though we weren't programming it, but configuring it for tasks, and implement a command acknowledge protocol, command AC, for those tasks. For example, something along the lines of go forward, go backward, turn left, turn right, and all single function programmable and very easily architected. By treating the sub as a kind of single entity and abstracting away from the multi-computer system that it really is, it reduces the program required for missions and reduces the programming required for testing in the pool and makes debugging much easier. Because if you have a baseline for what you're working on and you know that some subsystems don't need touching, you're free to work on the systems that have been recently changed or recently modified. For example, in missions testing, you know that your mission might need to be reconfigured. And aside from those pros, it also sediments a system of functions that should never be touched again, creates an API that you have to follow. This kind of structure is useful, especially in a competitive environment, because it forces developers to not make quick changes to long-used code in order to facilitate some or other function. So it doesn't trivialize the design process and make it kind of the Wild West when you're designing functions and what they do. So to implement such a system, we created many small sub-functions to complete larger functions. We would queue and monitor these spawn processes that each sub-function would complete, and abstract tasks like look for gate and supply it with radians, and have multiple sub-functions that take care of that, like buffer the image, and then take in the radians, and then actually analyze the image data, send each to the individual container that works on that sub-process. In our system, we had two main subsystems. So there's the mission subsystem and the AUV subsystem. And these two subsystems, one, the mission subsystem, primary goal is to tell the AUV subsystem what to do. The mission subsystem would say something along the lines of find the gate, do a spin, go underneath the gate, find the next closest obstacle, find the buoy, or in our case, do a 180-degree spin across the x-axis, etc. So that's the primary task of the mission subsystem. The AUV subsystem takes all of those commands and would allocate each of the individual containers working on those things. For example, the control container would take the command to do a 180 spin and architect that. But if at the same time you needed to do that 180 spin and say, take video and look for something else, you could do that because they're both containerized and they're both their own process. So you don't have to worry that the CPU is going to be trying to load balance between them because each container would have its own core allocated to it.
One of the changes that the software team wanted to focus on was finding a way to better improve our system's efficiency, primarily by implementing two computers. We found that when we allocated all of our processing power onto just our Jetson TX2, we dealt with bottlenecks and slow image processing. In addition, every year we try to, in some way, improve the image processing and object detection of our system. Especially with the murky conditions of the water, the competition, object detection is always one of the areas that is difficult to get working properly. So we're always finding different methods to tackle the issues of low visibility.
So our subsystems are primarily running Ubuntu, so both the Tegra and the Nano have Ubuntu operating system on them, heavily modified version for NVIDIA's case. But we can make use of the Linux containers infrastructure, so LXC, LXD, LXCD containers to facilitate virtualization and containerization. Docker can be used on the Nano, and it can be used on the Tegra with some modification. But it doesn't really play well with systemd and some of the other startup procedures that we want to use. So by having these two different management systems, it would just kind of create difficulties. So uniting everything under one single implementation would be the best, and that's what we aim to do.
This year, we first started by prioritizing being successful with the initial starting gate and the buoys. With the starting gate, we were also aiming to be able to do the coin flip as well as roll or pitch as we're going through the gate to get style points. We are fairly confident that we have been able to go through the right side of the gate depending on the coin flip, as well as be able to get some style points for one kind of spin. For the buoy task, we're also fairly confident that we have been able to pick the right buoy and be able to tap it. After this task, our plan was also to target the torpedo and dropper tasks. First, with the dropper, we believe that we have been able to attempt dropping a ball bearing for a dropper, as well as be able to aim a torpedo and shoot it at the board. More testing will have been needed in order to raise the confidence level of being able to shoot a torpedo through the bigger target, but we are sure that we have been able to at least aim and shoot the torpedo. If we were successful at these tasks, then we will have also attempted to navigate to the Octagon platform and rise there to end our run.
Now with the COVID scenario, testing was not an option. Our school shut down the pools just like many others, and it left a very tough challenge to overcome. We found communication was as important as ever. Between all teams, since we never see each other in person, we'd have to do many meetings over Zoom and communicate everyone on the same page to see what's next. As tough as it was a great learning experience in an ever-changing environment.
The team has made many efforts for creation of future builds and have made significant steps toward maneuvering the COVID-19 world and post-COVID-19 world by making testing and prototyping more approachable.
We are planning our approach to still provide hands-on experiences to our members by focusing on working on small robotics projects that can be tested at home and still have our members become familiarized with robotic systems that will be helpful for the RoboSub competition. This includes working on a small underwater vehicle that can be tested in a bathtub individually, and that way we can have a testing platform that will inform the electrical and software systems for future builds. Eventually, the goal will be to make a larger scale vehicle based on the lessons learned from these small robotics projects. We believe that through these methods, our projects will be more approachable for new members while still teaching valuable skills and overall create a stronger team.